Check it out now, y'all.
nanoHUB-U, online instruction.
Well, welcome to week 5. This is the first module, module 5.1. And this week we'll be talking about something a little different from what we have been talking about for the last 4 weeks, or in fact for most of this course. That is, one of the key ideas I've been using is this idea of an elastic resistor. That is, we have been talking about a conductor where electrons go straight through the channel without interacting with the surroundings. And the interaction with the surroundings, this heat generation, that is all confined to the contacts. And as I mentioned early on, this process of heat generation, that's somewhat different. That's these, what I generally call these entropy-driven processes. These are different, and usually what makes transport theory complicated is that ordinary mechanical things are sort of mixed up with these entropy-driven things. And what makes elastic resistors relatively simple is that entropy-driven things are spatially separated. Okay? And the picture that one could draw, here I've sort of taken our usual structure and kind of dissected it. So here's the channel. And we say that when an electron comes in, let's say it takes some amount of energy E1 from this contact, and N1 is the number of electrons coming in. And from this contact, I write E2 comma N2. Now, if you look at this contact, then this electron, when it comes out of here, it takes this energy E1, and another electron comes in from the battery. And the new electron that comes in around the electrochemical potential, and the energy associated is mu1 times N1. And this difference in the energy, E1 and mu1 N1, that is what comes in from outside. This is the heat, the energy that will come in from outside. Now, one thing I should mention is what I've drawn here are like reference directions, right? It doesn't mean that heat has to come out. In fact, usually what would happen, as you know, is when you connect a battery across it, heat would be generated in the contacts. What that means is that what I've written here would actually be negative rather than positive, for example. So the basic equations one could write down in general here. And so far, whatever I have drawn here is just like what we discussed in, I guess, part 1, week 5, when we were talking about thermoelectricity and we considered the heat current generated by electrons. And we talked about how heat comes in from the surroundings. So this is exactly what we had done then. And the only new thing that I'm adding to this is that instead of an elastic resistor, confining ourselves to elastic resistors, let's also add the possibility that there will be some energy exchange with the surroundings here, which also I'll write as E0. So this is the energy that is taken from the surroundings. Again, could be negative, so it could be given out to the surroundings. And the basic rules you can see is, if you look at this channel, N1 comes in from here, N2 comes in from here. Of course, one of them must be negative because overall there can't be any net inflow. This is all steady state. So N1 plus N2 must be 0. So that's equation number 1. Now, the next thing we could say is, well, I look at this channel. There's energy E1 coming in, E2 coming in, E0 coming in. Again, total energy coming in must be 0 because this has no way of storing that energy. Or otherwise, again, energy would be increasing. So we write E1 plus E2 plus E0 is equal to 0. And this you could call like conservation of energy. So what's total, steady state, what's coming in, let's say. Now, there is another relation that must be obeyed. And This is the one that's less appreciated, causes much debate. And that is that if you look at the total amount of energy that is coming in from the surroundings, you have E1 minus mu1 N1, E2 minus mu2 N2, and E0. The thing is that if you take E1 minus mu1 N1, that's the heat that's absorbed from the surroundings here. And this contact we are assuming is at some temperature T1. This contact is, we are assuming, at some temperature T2. Then this divided by T1 plus E2 minus mu2 N2 divided by T2 plus E0 divided by T0. So this is the heat taken in from 1, from 2, and from this intermediate region, that's the E0 over T0. All that must be less than or equal to 0. And this is the second law of thermodynamics, you see. And this is what we want to talk a little more about and understand where it comes from. Now, in one limit, you can kind of see what it says, though. And that is, supposing all three temperatures were equal, you see. So let's say there's T1, T2, T0, these were all equal, same temperature. Then what it's saying is that the total amount of heat that is taken in from the surroundings, if you look at the structure, this is the heat taken in from here, this is the heat taken in from here, this is what's taken in from here. That total heat taken in must be negative, which means overall it must be heat given out to the surroundings. Okay? And that you can kind of understand. You see, what you expect, of course, is in a structure like this, we will connect a battery. The battery is the one that will be giving energy to the system, and that energy will all be dissipated as heat. That's what normally happens when current flows. There's a I squared R loss, the joule heating. So in general, there is heat going out into the surroundings. And the energy, of course, comes from the battery. And that's what we normally expect. And what you don't expect is the reverse to happen. That is, you don't expect that you could make a device ever that would take heat from the surroundings and charge up your battery. You see, if it could do that, you have solved major problems. Because there's all this energy in the form of heat around us. And of course, when when heat engines were first developed, it took some time for people to come to the realization that, heat was also a form of energy. But it's a different form of energy in the sense that, see, you can take energy from a battery and dissipate it as heat, but you cannot easily do the opposite. You cannot take heat from your surroundings and charge up your battery. Although energy conservation-wise, both are equally possible. After all, energy is conserved. You're taking stuff from battery, making it heat, or you take heat and charge up your battery. Energy is conserved. But one is easy to do, happens naturally. The other one doesn't normally happen. Okay? And in a way, that's what this second law is telling you. You see, it tells you that if everything's at the same temperature, then the total amount of heat you take from the surroundings must be negative. In other words, you basically have to give up heat to the surroundings. You cannot just take heat from your surroundings and charge up your battery. That's in a way what it's saying. But then, if you have different parts of your system at different temperatures, then you could do some of that. You could take some heat and convert it into energy, and that's in a way what a heat engine is supposed to do. It works between two things at different temperatures. And this is again this fundamental law. Second law, which, as I said, causes a lot of debate, lots of discussion, a little less appreciated than, say, energy conservation. A lot more debate about it. Now, the point, when you hear that, you might say, well, all these rules all these things that we have been discussing in this course, are we sure it complies with this second law? And the answer is that one thing that you can easily check is that if you take an elastic resistor, that is, if there were no energy dissipation in here, if E0 is 0, like we did, that's what we've been doing in general. And as you know, for an elastic resistor, we wrote the current flow as F1 minus F2. So if F1 is greater than F2, then electrons will flow from 1 to 2. And if F1 is less than F2, it will flow the other way. That's the basic relation we have obtained for elastic resistors. I mean, this you can get from very simple arguments as we did in part 1, or more, even when you do quantum transport, current was still proportional to F1 minus F2. And the thing you'll notice here is that if you drop this, then you basically get this relationship, and E1 is the total amount of energy that is coming in from contact 1. You could write this in the form of energy of an electron times the number of electrons. So you could write it as epsilon n1. Similarly, you could write this as epsilon n2. So what this says then is, you could write it as epsilon minus mu1 times n1 over T1 plus epsilon minus mu2 times n2 over T2 is greater than or equal to 0. And of course we know that n1 plus n2 is equal to 0, total amount of electrons coming in, 0. So we could write, instead of n2, I could write minus n1. So what you get then is that epsilon minus mu1 over T1 minus epsilon minus mu2 over T2 times n1. This minus is because I replaced the n2 with a minus n1, and that's then less than or equal to 0. Now, what you can see easily is, you see, if, let's say, F1 is bigger than F2. Now, what is the Fermi function? The Fermi function, as you know, is given by this 1 divided by exponential of epsilon minus mu1 over kt1 plus 1. So if F1 is bigger than F2, it means this quantity must be less, because unless it's less, the denominator won't be small. You see, if this is big, it means the denominator is small. And so this must be less than that if F1 is greater than F2. So this is less than that, which means this quantity is negative. And in that case, N1 is positive. Electrons go from 1 to 2. And so the overall product is negative. And if F1 were less than F2, then of course this would be positive. But then electrons would flow the other way. And so N1 would have been negative. Anyway, so the bottom line is that for elastic resistors, whatever we have done is easily in compliance with the second law. But what we really want to talk about is now the more general case, you see, when energy is exchanged even inside the channel and you have this inelastic transport, what is the general principle that we need to make sure of so that second law would be satisfied? And the basic rule is the following. That is that any time you have a contact and you take some energy from it and some electrons from it, so consider that process and consider the reverse process. The reverse process where you dump energy into the contact or number of electrons. Note that this plus and minus are kind of defined with respect to the system that takes the energy. So it's like I'm writing E is positive means the energy goes out of the contact somewhere, whereas negative is going in. And the basic rule is simply that the probability of this first process to the probability of this second process should be equal to, this ratio is minus E minus mu n over kT. That's the basic thing. See? So next module we'll talk about, where that comes from, why the ratio is always like this. But the main point I want to make is, what you can see, check easily, is that if this relation is satisfied, then it would also make sure that the second law would be satisfied. How do we know that? Well, it goes something like this. Consider the process that we have drawn here. You're taking E1, N1 from here, E0 from here, and E2, N2 from here. So the overall probability of something like this happening would be P E1, N1 times P E2, N2 times P E0. And now consider the reverse process. The reverse process where instead of taking these in, the way I've drawn it, it goes out, all the negatives. So exact reverse process. And the point is that if the dominant process is one where the way I've drawn it, then this ratio must be greater than or equal to 1. In the sense that if it were equal to 1, then of course this process and its reverse are equally likely, which means it isn't quite happening. It has to be a little more than 1 in order for the process to go on. And as long as these ratios of P's obey this equation, see, I can write this ratio in the form, take this out, and take this ratio, write it as exponential minus E1 minus mu N1 over kT. And then the next one is exponential minus E2 minus mu 2 N2 over kT. And then exponential minus E0 over kT. And the total product is greater than or equal to 1. So what that means is I could write this as exponential of negative of E1 minus mu1 N1 over kT plus E2 minus mu 2 N2 over kT plus E0 over kT. That's greater than or equal to 1. 1. Now this exponential has the property that exponential of 0 is 1. Exponential of a negative quantity is less than 1. Exponential of a positive quantity is more than 1. So if this happens to be more than 1, it means whatever I have in the exponent must be positive. And since I have a negative sign in front, it means this quantity must be negative. Oh, by the way, I guess I forgot to distinguish between the 3 temperatures, because in general, these 3 contacts have 3 different temperatures. So I'll put a T1 here, T2 here, and a T0 here. So that's T1, T2, T0. And the thing is, this sum must be then less than or equal to 0, and I can cancel out the K's, and that's basically the second law I had stated earlier. I said that the second law says that the heat you take from one contact divided by temperature 1, heat you take from another by temperature 2, heat you take from the third one divided by temperature, all that must be less than or equal to 0. So basically what this shows then is that as long as whenever you are making up this, any theory of transport, you're trying to describe different processes, the thing that you have to ensure is that whenever you take energy or particles from a contact which is at equilibrium with some chemical potential and some temperature T, the process of taking things out from it and dumping it in. So this, what you might call absorption and emission. That is, here I'm absorbing things from the contact, here I'm emitting things into the contact. Absorption to emission must have this ratio. And if particle exchange is not involved, if it's just energy, then you could write PE over P minus E is equal to E to the power minus E over KT. So what it says is absorption to emission ratio has this form, which means it is always a little harder to absorb than to emit. And as long as that is satisfied, the second law will be satisfied. So in the next module then, we'll talk about why absorption is harder than emission.